Alright, I am so excited for today. We are finally talking about one of my favorite topics, which is graph theory. So, graph theory is the study of graphs, which for now let's just think of as collections of nodes or vertices and edges. So over here I have a picture of a graph, and we'll get into some more formal definitions later on, but first I just want to talk a little bit about what graph theory is and why we care about it. One thing I particularly like about this topic is that it strikes a great balance between tangible, manageable questions, like how many edges come out of a certain vertex, or can a graph be drawn in a flat plane like we have here? And so it strikes a balance between these and real-world important applications. So a lot of the questions that we'll be asking in this class are fairly small scale. We're talking about graphs that we can draw, that we can really wrap our head around. But much of the strength of graph theory comes from the fact that it can be scaled up to incredibly large and complex graphs that are representing information that we can't really wrap our heads around directly. But many of the tools that we'll be talking about scale up very well. All right. So say that we have a graph or a picture like this representing the, let's say, Facebook network. So if each vertex is a user, and there's a connection between two users if they're Facebook friends, then the graph in question is incredibly large. Millions and millions of vertices, and there's no real way to wrap our head around this picture. Even to look at it, it just is too complex to really see. That said, computers can do a lot of the tools or the techniques that we'll be talking about on bigger scales. Most of the questions we'll be asking in this class are working with these small scale graphs that we can draw, that we can wrap our head around. But I wanted to say up front that the reason we're asking most of these questions is because these types of things scale to the more common real world applications. And many of the skills that we learn, or many of the techniques, are actually used in these big data questions. So to mention a few of these examples, sociology, anything involving social networking, anything involving social dynamics is often very well represented by using some sort of picture like this. We can use graphs to represent different components in words, so we can talk about the relationship between words by putting words in a graph. Maybe each word is associated to a vertex, and there's an edge connecting words if they're related in some way. And then we can study the graph itself and ask linguistics types of questions about the graph. This crops up in biology, both micro. Maybe we are representing genome changes, maybe an edge represents a mutation, each vertex is representing a particular gene sequence. Maybe we are talking about the behaviors of animals in a more macro sense. In physics, anytime we're doing almost anything with quantum anything, graphs are usually a good way of representing what's happening. We can use graphs to talk about chemical structure. We've got atoms and their bonds. I really could just go on and on about different situations in which graphs make for a helpful model to represent some part of a system. Anytime we have any sort of dynamics, anything that's changing, often a graph is a very helpful way of thinking about the question. Before we can get into any of these, we need to first talk about what a graph is. And I started off with a very vague definition, I didn't even write it down, that a graph is this collection of points or dots or vertices, and they're connected by lines or edges. So first up is a rigorous definition of what exactly do we mean by a graph. Our informal definition of a graph is that it's simply a network or a collection of vertices that are connected by edges. When I'm working with graphs, this is my mental impression of what a graph is. That said, it does help to have a more formal definition because there can be a lot of ambiguity about what exactly we mean by this. So here is a picture of a graph, and we've labeled a few of the vertices with labels. What would happen if we changed a few of the labels? What if we made this vertex C and this one D? So by swapping the labels, have we changed the graph? Here's another question. What if we drew this in a slightly different way? So what if we had the same graph over here, except maybe this edge is drawn differently? Do we still have the same graph? Can we draw a graph where the edges are bent? Can the edges wrap onto themselves? Can they cross over each other? Can we have duplicate edges between two vertices? The answer to all of these questions is, well, it depends. Sometimes we can, sometimes we can't. It depends on what we're using it for. It depends on what type of graph question we're asking. Right. To avoid all of this ambiguity, we're going to use sets to define what a graph is. So our formal definition of what a graph is that it is an ordered pair of sets. So a graph G is a collection of two different sets V and E, which we think of as V being the collection of vertices and E being the collection of edges. That said, as far as this definition is concerned, we just have two sets as long as they have the property that the elements of E, the things that are in this set E, are two element subsets of the set V. Here's an example. Let's say that V is the four-element set ABCD. Great. Now, in order for G to be a graph, in order for the ordered pair V comma E to represent a graph, it better be the case that the things that are in E, the elements of E, are themselves sets, more specifically that they need to be two-element subsets of V. So everything in E better look like a set that contains two elements, each of which come from V. So that's the case here. We have A and B, B and C, A and C, C and D. Well, none of this feels like a graph to me at first glance. Early on, we said that graphs are pictures that look like this. We have these points and we have these lines connecting them. But at their core, these are really two different ways of writing really the same ideas. The vertices in each, the collection of vertices are the same, and the collection of edges are the same. We have four vertices in this picture, four vertices here, and the edges that we have AB, we have BC, we have AC, and we have CD. So the edges line up, the vertices line up. So we like to think that this picture is a graphical representation of this formal graph. The formal definition of a graph is a collection of sets, but this isn't an easy way to think about what's happening. Even for this relatively simple example, it's not easy to wrap your head around what's happening looking at this using the sets, but I think the picture does a much better job of representing what's going on. So for the most part, we will use pictures to talk about what these moving parts are, but as far as the formal definition goes, and as far as computers that are working with this are concerned, what a graph is a collection of sets. All right, before we jump into too much of this, there are a few definitions that we need to talk about. The first couple aren't going to be discussed much. We're going to assume in this class that most of the time whenever we say a graph, we're talking about a simple graph. So a simple graph is one that behaves well. It doesn't have one of these two problems to it. So for example, if we have two vertices, we don't want our graph to have multiple edges connecting those two vertices. So we would say that this piece of a graph, or this graph, is not a simple graph. Sort of related to this, if we also want to specify that no edge can leave a vertex and come back to the same vertex. If either of these things happen, then the graph is not simple. So most of the time, I will remember to specify that we're working with a simple graph, but in general in this class, we will assume that all of our graphs are simple. We'll also usually be working with graphs that are connected. So two graphs are connected if you can get from any vertex to any other vertex by walking along edges. Here is an example of a graph that is not connected. In a sense, graphs that aren't connected are sort of separate graphs themselves. Given our set definition of them, this can certainly be considered one graph that isn't connected. But most of the time when we're working with graphs in this class, we will be working with connected graphs. That said, there certainly are things to be said about disconnected or not connected graphs. And our third property of graphs that's worth mentioning now is that a graph is planar if we can draw it where the edges don't cross each other. So every graph that I've drawn so far is planar. This one, however, is not planar. Notice how we have edges that are crossing each other. If we draw this on a flat plane, then we have to have edges cross each other. And we'll be talking a lot more about which graphs are planar versus which graphs are not planar. So here I have 4 different graphs or representations of graphs that are different. Like, we have different labels that make something different. We use a different convention. Maybe we're talking about the actual set formal definition versus a pictorial representation. So these are all different, but at their core, they're talking about the same graph. So functionally, all 4 of these pictures are really talking about the same thing. So we'll say that these are all isomorphic, meaning that functionally they count as the same thing. Changing the labels doesn't really affect what we're talking about. Moving the representation around, maybe introducing crossings, doesn't really matter. And switching back and forth between our set notation and a graphic notation still doesn't really change the underlying structure. So the idea here is that isomorphic means that the 2 graphs the 2 pictures in question are essentially the same thing. So we'll say that 2 graphs are isomorphic if they line up with each other well. In other words, 2 graphs are isomorphic if there's some function that identifies the pieces or the vertices and edges of one graph to the pieces of the other graph. So formally, the way that we'll say that is that 2 graphs are isomorphic if there's some function between the set of vertices that is 1, 2, and 1 to 1. Now, when we were originally talking about functions being 1, 2, and 1 to 1, I would often draw this picture where we have some number of elements in that first set and some number of elements in the second set, and I would say that the function is an identification of the elements in the first set, the elements in the second set. The function itself is the collection of arrows that tell you where each element goes. And at least for finite sets, when you have a function that is both 1, 2, and 1 to 1, then everything lines up well. We can say this piece really is equivalent to that piece, or it's matched up with that piece. Okay, so when we say that we want there to be some function between the 2 graphs, where the function going on the vertices is 1, 2, and 1 to 1, this is possible when the 2 sets in question have sort of the same structure. So that's what we're after here. So in this example, we have 2 pictures of what ends up being functionally very similar graphs. These 2 graphs end up being isomorphic because there is a function that meets these criteria. We also want it to be the case that edges get brought along for the ride. So if we have some edge in the first graph, so here's our first graph, here's our G1, CD is an edge. We want it to be the case that whenever our function does, if our function is telling us where each of these vertices go, we want it to be the case that the edges come along for the ride. Since CD is an edge, we want it to be the case that f of C and f of D is also an edge in our other graph. So here's an example of a function that meets these criteria. Let's say that D goes to 4. This is the vertex that's off on its own. That should go to the vertex that's off on its own. C is the vertex that connects to this lonely vertex. So that should probably be 1. So let's say that C goes to 1. And then let's send B to 2 and A to 3. All right, so using arrows, I've specified a function that is 1, 2. All of the vertices in the second graph are targeted. It's 1 to 1. None of them have multiple arrows pointing at them. And it should be the case that every edge in our first graph, so let's take the AC edge, corresponds to an edge in the other graph. So since A went to 3 and C went to 2, and since AC is an edge, it better be the case that 1, 3 is also an edge. And it should be true vice versa. Edges over here should correspond to edges back in the original graph. So this is a long-winded and formal way of saying that 2 graphs are essentially the same. They're isomorphic. If we can get from one to the other by maybe drawing it in a different way, by maybe changing labels, but without changing any of the fundamental structure of which edges are connected and what the structure of the graph is at heart. One word on notation, if 2 graphs are in fact isomorphic, then we use this symbol to say that they are isomorphic. So this may be recognized as the congruency symbol. 2 graphs G1 and G2 are essentially the same thing. They are isomorphic when we write it like this. So here's a couple graphs that are kind of clearly not isomorphic. These 2 graphs are fundamentally different because, well, they have a different number of vertices. In order for our function to be 1 to 1 to 1, it better be the case that the number of vertices lines up on both sides. Similar logic holds for the total number of edges. For this left graph, we have 2 edges, the right graph we have 3 edges, so there's really no way that they can be isomorphic. However, let's take a look at these 2 graphs. So we have 5 vertices on each side, and we have 6 edges on each side. Go ahead and pause this video and see if you can work out if these 2 graphs are isomorphic, and if not, why aren't they isomorphic? Is there any fundamental property that you can pick out that makes these 2 different? And that brings us to our last definition for today, and that is that the valence of a vertex is the number of edges that leave it, or that come to it, or that meet at that vertex. So for example, our D vertex here has valence 1, whereas C has 3 edges coming out of it, so it has valence 3. And one thing that we can write down for a graph is called the valence sequence. Well, the valence sequence for this graph is 1, 2, 2, 3. We're just listing out the valences of each of the vertices. All right, that's it for today. Sorry for throwing so many definitions at you, but moving forward, there will hopefully be less. This sort of often happens when you start a new subject. But yeah, there is plenty more to be done about all these. There's a lot of questions that I have for you all to work on your own. And yeah, we'll be doing graph theory for the next few weeks, and then we will be transitioning towards some gerrymandering topics, which I, for one, am very excited about as well.